so that don't worry, we are already, we are still here.
All right, I see the faces there. Thank you for having me. I'm honored to be invited here. I know it's at the end of your day and end of your event. I appreciate you being available for me to share. So I'm glad to present a little bit about what we're doing in the U.S. and the Department of Energy funded research. Unfortunately, I wasn't able to listen to all of the talks you've heard the last couple of days, so there might be some repetition. But I'm glad if you have any questions or comments to go ahead and interrupt me. Let me know. So let's see if I can get everything to work here. All right. So do you see my second slide now with my picture? Yeah. Okay. So this is our team here. This is, as Simone mentioned, the U.S. Department of Energy has funded some of this work under the LWRS program, which is the Lightwater Reactor Sustainability Program. The goal of this office in the DOE is to support the continued operation of existing nuclear power plants in the U.S. So I'm at Pacific Northwest National Laboratory, that's in Washington State, in the northwest part of the country. And there's a couple of tasks in the LWRS program under the materials research pathway. Tom Rosseel, who heads that pathway, is located at a different national lab, Oak Ridge in Tennessee, in the southeast of the country. And he leads the pathway, which includes other materials like metals and concrete. But the cables, we have a cable aging and cable NDE, non-destructive evaluation tasks, both led at PNNL with collaborators at Oak Ridge. So Lightwater reactor sustainability. So in the US, we have approximately 90 operational reactors right now, which constitutes, so these numbers change, unfortunately are changing over time, but the US nuclear power accounts for approximately 30% of the electricity generation in the world, and around 20% of the electricity generation of the nuclear electricity generation in the world, and 20% of the electricity in the US. So the average age of US reactors is about 39 years. And the context in the US, I'm not super familiar with the context in Europe, but in the US, plants were initially given an operating license, a license to operate for 40 years. They were designed and qualified to operate for 40 years. Our regulatory agency in the US is called the NRC, the Nuclear Regulatory Commission. So each utility that operates a plant has a license to operate that plant from the NRC, and those were 40-year licenses. And with average age 39, there are many plants that are older than 40, and almost all the plants, all the reactors have received license extensions to operate up to 60 years after they're designed for 40 when they were first built. I don't know if anyone imagined that they would continue to be used after 40 years. They were probably imagined they're going to just build new ones and retire those. But unfortunately, in the US, we're not building new reactors very rapidly. There's only the two that are currently under construction are going to be the first new reactors to come online in the last more than 30 years. So in the US, we're having a hard time building new reactors very quickly. And the fact that we get 20% of our electricity from nuclear power means that we're motivated to keep using the existing plants. So most plants have been licensed, have been extended, operate up to 60 years, so-called license renewal, we call it. And as of 2018, the first plants have been, applications have been approved to opt for subsequent or second license renewal to operate up to 80 years total. So they're renewing the licenses at 20 years at a time. So these originally planned 40-year plants are now licensed to operate up to 80 years. So the one challenge is this design life of the plants. Another challenge is with low-cost natural gas, for instance, in the U.S. in recent years, in some markets in the U.S., there's different markets in the U.S. Some markets where the costs of electricity are not regulated, they're allowed to be competitive. It's hard for nuclear energy electricity to be cost competitive with natural gas. It costs more to generate kilowatt hours from the nuclear than it does from some other competing technology. So there's a couple of challenges for sustaining a light water reactor electricity. So as you're familiar, before this course or in the last few days, you've heard probably a lot about the fact that electrical cables are an integral part of nuclear power plants. In each power plant, in the US, we have 2/3 of the plants are pressurized water reactors. We also have boiling water reactors. And in each plant, there are thousands of kilometers of electrical cables, many types and sizes of cables. They run throughout the plant to control sensors and safety systems and power. And there's the nerve system and a control system of the whole plant. And ramifications for cable failure or cable malfunction can be significant, especially when the cables are powering emergency systems. So it's important that they are reliable and continue to operate. So as plants, as I mentioned, they were licensed for 40 years. As they've received license renewal to operate for longer, plants have had to institute what we call cable aging management programs, or CAMPs, cable aging management programs, to make sure that that the cables that are decades old continue to operate reliably. And so these cable aging management programs have to inventory the cables and understand which cables are at risk of outliving their useful life, and what are their status, how often they need to be tested, and how to be tested, what situations they're in. Now, a challenge is that most cables lay in are not easily accessible. They go through concrete walls. They're up on cable trays. They're not easily accessible, and often you can only access the cables at the terminations to test them. So that's a challenge with testing all the cables in the plant. There are many cables, many more than can be tested every outage. Usually in these US plants have a refueling outage about every year and a half or 2 years. And there's a short time when the plant shut down and every area can be accessed for testing. But usually cables can efficiently be tested just from the terminations and not all along the cable. So there's a need for effective and efficient cable monitoring technologies, like I'm sure you've been learning about last few days and just getting practical in moments ago. So the objective of our research that's funded by the DOE is to understand the effects of the material systems, the materials in the cables, the histories of the cables, and the environments that they're in. Some places in the plant they're going to be exposed to gamma radiation, some places elevated temperatures. To understand those effects on the degradation of the cable system, and specifically the polymer insulation. We also seek to understand the limitations of accelerated aging in the laboratory, and to support modeling, predictive modeling of the remaining useful life of cables, and the condition and understanding signals from condition monitoring. Now, as I mentioned, the license renewal, so that cable aging management programs, each time there's an outage or throughout the plant's operation, select cables are tested at a time on certain frequencies, not every cable. So they pursue a strategy called type testing, where if you try to find the cable that's in the most severe condition or the most susceptible to aging, and test those first, and then you can extrapolate results from similar cables to the one that you're testing. So what I want to emphasize is in the original qualification, for 40 years qualification, cables, safety-related cables were qualified for 40 years. And the way that they qualified the cables before the plants came online at the beginning was to do accelerated aging in the laboratory at elevated temperatures and high dose rates, accelerated aging to impart effective 40 years of aging on the cables, and then do design basis event testing, loss of coolant accident testing to see if the cables will survive that. And if they had the 40 years of equivalent aging and then they survived the testing, then they could be qualified. But as I'll mention, that process that was used to get the 40-year qualification life is being looked at with greater scrutiny, more detailed, as we try to take these cables and these plants beyond their original intended life to 60 and 80 years. So our objectives are also to support and develop methods for condition monitoring, like dielectric spectroscopy, frequency domain reflectometry, and others. to support a risk-based inspection rather than time-based inspection. If you test cables that you have reason to believe will be degrading, it's more efficient than just testing them based on the calendar. And we'd like to, additional goals are to develop technologies to mitigate cable aging, like cable rejuvenation, treatment of cables to extend their life. And with the cost pressures, the goals of these NDE techniques are also to reduce the operating costs in maintaining plants. So this schematic shows, this is from the Nuclear Energy Institute industry group in the US, and it shows the continuous improvement of aging management programs. And just to illustrate cable aging at the DOE supports other organizations like EPRI, Electric Power Research Institute, that help the utilities to do their cable aging management. We support the development of technologies and understanding of the aging and monitoring technology issues. So as you know, the part of the cables that degrades most readily is this polymer insulation, and it's the environment like heat, radiation, moisture, chemicals, vibration, stresses in operation that cause chemical changes, molecular changes in the polymers that can lead to material changes like embrittlement and dielectric behavior changes that affect the performance of the cables. So my understanding is that there are similar materials used in European plants, but not necessarily the same. So in U.S. plants, almost all the cables are XLPE, crossing polyethylene, or EPR, ethylene propylene rubber. We have very few polyvinyl chloride insulation examples. For instance, there's also silicon rubber, especially at higher temperature locations, but most cable insulations in the U.S. are XLPE or EPR. And there's a variety of manufacturers. These are some of the most common manufacturers found: Rockbestis, Brandrex, Raychem, Anaconda, Okanite, BIW, Carite. And so the context of Lightwater reactor sustainability cable program is to understand the aging of cables as they get old. So many of these cables were manufactured in the 60s, 70s, 80s, and a lot of these companies are not in existence anymore. And if they were, the material formulations are proprietary. Obviously, they've been improved and changed in decades past. So it's really a forensic-ish situation. We're trying to understand how these old remnant materials will continue to behave. So to summarize the cable aging management, the aging is going to behavior and the tools to assess that, to quantify that, depend on the components in the cable system, the construction of the cable, and the operating environment. So for instance, if there's the temperature that the cable is exposed to, the radiation, that's the environment, the materials, if it's XLPE or EPR or PVC or silicone, and then the construction is going to depend if it's shielded or not shielded, if it's a multi-conductor, if it's a medium voltage cable and it's very thick insulation or low voltage and thinner, those factors affect the degradation, but also the ways that you can assess it. In the last practical, you're just doing some of the questions about the bonding of insulation or the connection of, or the orientation of conductors, insulated conductors next to each other. Those things affect some of the tools that can be used to assess the condition of the cable. So all those factors, along with the time, how long they've been in service in those conditions, affect the aging degradation, and how we can quantify that and monitor the condition. Ultimately, we want to know how cables are still behaving, are still performing their function safely, and how much longer we can expect them to continue to do that. Changing out cables, you might think that one simple solution to dealing with these old cables is just replace all the cables with new modern cables, but that would be with thousands of kilometers, that would be cost prohibitive. And so it's fine to replace cables when they need to, but the real challenge is to know which cables need to be replaced and when, so they can be planned for and not fail unexpectedly. There's so many redundant systems. There's not it's not much of a concern that you're going to have the catastrophic failure and a safety issue for the public if a cable fails, but it's certainly going to affect the operation of the plant and the generation of electricity from that plant. So let me talk about a couple of the tasks there. The cable aging task, one of the areas that we focused on in the last several years are these identified research and knowledge gaps related to this subsequent license renewal. As plants renewed their license from 40 years to 60 years, and then they started to approach SLR to go from 60 to 80, the situation was with their initial license renewal to 60 years, they went back, and I think the regulators and the licensees went back and looked at the process that they went through to do the accelerated aging and testing and qualifying the cables, and they realized that there were a lot of margin in that and a lot of conservatism in that calculation. For instance, before they had the operating experience, they thought that cables might, in 40 years, they might be exposed to 50 megarads of gamma radiation. Turns out that they're exposed to much less than that, maybe 13 megarads at the most in general. And then temperatures, they assumed higher temperatures than are actually observed. So they were able to go back and say, okay, we were conservative in our estimate for 40 years, and actually it's fine. These cables can last 60 years. Most cables can last 60 years. Some have we know about have problems, but in general, 60 years is fine. But when they went back to renew their license to 80 years instead of 60 years, the NRC wanted a closer look. And so one of those closer look is what assumptions were used during that qualification process. You know, many assumptions were used, such as we do some accelerated aging in the laboratory, and it represents what happens over 40 years in the plant. Okay, that's a big assumption. So some of the knowledge gap, well, almost all the knowledge gaps have to do with the questioning those assumptions that were made during that process. So the colored knowledge gaps above are the ones that we've been focusing on, and then some other knowledge gaps, such as what are the actual plant environments, what are actual gamma dose rates and temperatures in operation. Some of those other knowledge gaps have been addressed by partners like EPRI or ones that we haven't gotten to yet. So I'm just going to highlight a few because of the amount of time we have today. I might show some results, and maybe I'll go through those quickly, but I'll just give some overview here. And please, if there's any questions, go ahead and stop me. Any questions at this point? All right. So let me just describe some of these knowledge gaps. So one of the questions about activation energy values. So the way you do put 40 years of age on a cable before you test it is if it's main degradation pathway is thermal degradation, you can just apply a higher temperature and it ages faster. You use a Arrhenius process to calculate how many years, equivalent years it represents when you do that laboratory aging. But the question is that activation energy that you determine through a series of elevated temperatures, activation energy might actually be temperature dependent. And the aging behavior of a cable in a plant over decades at say 40 or 50 C might be different, or lower temperature might be different than what happens in laboratory when you're doing 165 C accelerated aging. So that's a complication because it's hard to do a 40-year experiment to see how the cable is operating, or even a 10-year experiment. When you're limited to months or maybe a year or two on an experiment, you have to do some extreme accelerated aging, and the activation energy may not be the same in those different conditions. Another knowledge gap we call DLO, or diffusion limited oxidation. This came about because it was observed that if you age a polymer very rapidly, such as at a high temperature, many of these polymer insulations are rated at maybe 90 degrees Celsius. But if you put that in the oven to try to make it age quickly at 165, 180 C, what happens is the exterior of the material ages very rapidly, and that aged crust forms on the material, and that prevents oxygen from penetrating into the interior of the polymer sample, and it limits that diffusion of oxygen in. And if your major reaction is the oxidation of the organic polymer, then the aging occurs in a different way than it would over a long time at a more mild condition. And you can actually underestimate the effect of that aging because the interior of the polymer sample is actually protected by that rapidly aged exterior. I kind of think of like you have aluminum and you cut a fresh surface of aluminum and it reacts very rapidly to make an oxidation layer, and then the rest of the solid doesn't oxidize because of that protective layer on the outside. That's I think it's of it as a similar process. Okay, next assumption is dose rate effects. Like I mentioned, if they 50 megarads were assumed, or is that 500 kilogray were assumed as the dose over 40 years, that was during qualification, that was often applied all at once at a high rate, like 1,000 gray per hour or more. And the question is, when you apply a total dose over a few hours versus over a low dose rate, maybe 10 gray per hour or 1 gray per hour over many years, do you get the same degradation mechanism? So that's a dose rate effect. Some of the other questions about those assumptions similarly deal with the combination of radiation and thermal aging. So during that qualification, it was common to do your accelerated aging by having your cable samples that you're qualifying at an elevated temperature in the oven for some number of days. So maybe at a 150 degrees for 21 days, and then expose them to your expected gamma dose, 50 megarads, and then do the qualification test. Well, there's a question as if you're applying radiation stress and thermal stress at the same time, it might activate different mechanisms than if you apply them sequentially. So that's a concurrent or simultaneous versus sequential. And a similar related knowledge gap is become known as synergistic effects. Is the question is if you're applying gamma radiation and heat at the same time, you might have some different mechanisms than you would if you applied them separately. So somehow they work together. That was a question, is whether or not these effects, these order of exposure matters, or if they work together. All this relates to if we could expect those cables initially qualified, how long we can expect them to last. So for instance, if we had some of these effects like DLO and we overestimated their performance to that accelerated aging, the concern is that maybe when we thought they were going to last for hundreds of years, and it turns out that they only last for 50 years, then maybe they need to be replaced before we relicense the plant to operate to 60 or 80 years. And the final one is if the inverse temperature effects it's been observed in the laboratory in some cases that gamma radiation is more destructive to the polymers at lower temperatures counterintuitively than it is at higher temperatures. So normally in long-term plant operation, the temperatures would be relatively mild, and if cable polymers are exposed to gamma radiation under the mild conditions, the concern is they might age more rapidly actually than when you're trying to do in the laboratory at high temperatures at radiation at the same time. So those are some of the knowledge gaps that the cable aging program has been addressing. In the cable aging program, understanding how materials age with exposure is also important for interpreting your condition monitoring, your cable NDE signals. So now I have some recent results to share, and maybe I'll try to go through these pretty quickly, but here's an example where we're looking at the knowledge gap of activation energies. And so in lifetime prediction, as you may have been already talking about last couple of days, we want to understand how these materials are going to perform long into the future. So we can't do a long experiment. We have to do some kind of a shorter term experiment and extrapolate those results into the future. So one reason to want to have accurate activation energy is so that you can do that and understand if your activation energy is actually temperature dependent. So you do your quick experiments at high temperature, how to extrapolate that to long exposure at low temperature, you have to understand the relationship between activation energy as a function of temperature. The other reason why you might want to have sensitive measures of changes, so a lot of times this material property that we're looking at, often in the cable realm, it's tensile elongation of break is used to track aging, right, of these elastomers. So another challenge with doing accelerated aging is that if you're trying to use as mild temperatures as you can to best replicate the in-service aging, the problem is that what you're measuring, like elongation of break, might not change very rapidly until well into the aging. So it's in that case, we're motivated to find sensitive measures of aging, that things that change predictably over time, and they change from early on. They don't have this kind of a plateau period of aging before they finally fall off. If they change early on, you can extrapolate from early aging to long-term aging accurately, because of the practical experimental time frame is short compared to a service lifetime. So the references I'm making in this presentation, most of them are to PNNL reports that are available on the web. And if they're recent, then they will be available later, if not yet. So I'll go through this quickly. So that in the thermal and radiation aging as well, for these polymers, the major mechanism of degradation is oxidative degradation, where the polymers, the hydrocarbons, are reacting with oxygen in the atmosphere, and the reactive radicals get generated in the polymer from the radiation or from the heat, and those react to break up the polymers and change the mechanical properties. The major concern is that they embrittle the polymer, and then if there's a accident in the plant, that they won't perform their function. So the oxygen gets consumed in that reaction. So one way to a measure of aging that's been proposed that might track closely with aging, even at mild aging, is the consumption of oxygen in this reaction. So if you're having this oxidative degradation, it doesn't happen without consumption of oxygen. So the rate of oxygen consumed should, if we're able to measure that, should tell us about what's happening. This is a very laboratory experiment because you can't measure oxygen consumption in situ in a plant, but you can in the laboratory. So I'll just briefly describe the experiment we did this last year. We looked at a couple of different insulations, XLPE and EPR examples, and these were removed from cables that had a hypalon or chlorosulfonated polyethylene jacket, but we remove just the insulation, and we loaded insulation samples into a vessel with a known atmosphere. We're able to load it with known simulated air atmosphere, and then expose the vessels to the stress, and then we can measure the changes in that atmosphere to quantify how much oxygen was consumed. In this example, these loaded vessels with the polymer insulation samples. So these were insulations we call straws, in which the metal conductor was removed so that we could perform tensile measurements on them afterwards. These straws were loaded in these vessels. They were sent to Sandia National Laboratory, another DOE laboratory in southwestern part of the country, for gamma exposure. So in this case, it's just at room temperature. They're exposed to gamma radiation at a series of 3 different dose rates. And then there's many vessels here because they were over time. They were removed, so we have a series of different doses at different dose rates. And here's the data at different dose rates, the oxygen consumption. And as we observed, the oxygen consumption occurred at a very, very constant rates under the conditions we employed. So the pressure of air, I think we had 2 atmospheres of air in the vessels. In the volume of vessels versus the volume of the polymer, we saw a very linear behavior. So the oxygen consumption was greater at the higher dose rate and lower at the lower dose rate. The amount of oxygen consumed is plotted here versus time. So this measure has a benefit of it's sensitive from early on, and in this case, we didn't see a dose rate dependence. The oxygen consumption was directly proportional to the dose received. So we measured these materials in several different ways. We looked at the change in mass of the materials, which also tracked closely with dose. We looked at we measured the density of the materials, and it was a surprise to me that we did not observe change over the parameters explored, which were up to over 30 megarads, 300 kilogray. We didn't observe changes in density, trend in change in density at all for these materials. I was kind of surprised by that. I thought that we would, but we didn't see that. We measured carbonyl index. This is a Fourier transform infrared spectroscopy technique to look at the formation of carbon-oxygen bonds on the surface of the polymers. We saw a trend with dose, and we measured, for one of the insulations we measured, the XLP was a white-colored insulation. So an area that we've developed in the last few years that's been fruitful is quantifying color change. Works better for light color materials than dark color materials, but color change actually tracks pretty well with polymer aging. So we measure the color change of this insulation with exposure, and it's very surface sensitive technique, and we saw a dose dependence. It wasn't as linear as some of the others. So this, just in summary, this is normalized properties: oxygen consumption, mass change, density, carbonyl index, and yellowness index for XLP and EPR with exposure to different dose rates of gamma radiation. So this is versus total dose. And so some of the properties like oxygen consumption and mass change were very linear from the beginning. So they proved to be good candidates for sensitive measures of aging, whereas the green dots, green squares here are more all over the map for density. So density didn't end up being in this experiment a good measure as the others. So unfortunately, oxygen consumption and mass change, those are limited to laboratory techniques. You can't, it's difficult to measure that for insulation on an installed cable. But this effort showed that those are valuable tools for doing accelerated aging. And the understanding is that if we then try to do accelerated aging at a mild conditions like 90 degrees C, 100 degrees C, where it's going to take many years to come to completion of aging, we can maybe get those early data points and extrapolate the aging from at a mild condition at a reasonable amount of time. So that's it for that section. Any questions on the sensitive measures of aging task? Okay. I can see you there still. You're in the dark now. So I'll talk about another recent effort was to look at this knowledge gap related to diffusion-limited oxidation. As I mentioned, this is when you have rapid aging at the edge of a sample, and it actually prevents aging from the interior of the sample, which can lead to a misunderstanding of the when you try to extrapolate accelerated aging to mild service conditions. In this case, we looked at a few different materials: an Anaconda EPR, Rockbestos XLPE, and a Brand Rex XLPE. These are just summary plots that shows at different temperatures when we did the aging. This is through the thickness of the material. These are average results of the thickness of material and the color change. So we saw in this example of EPR on the left, at a lower temperature of aging, it was more homogeneous through the thickness. But as we increased the temperature up to 165 degrees C during aging, we saw more of this effect of more rapid aging at the edge. We did observe, so similar results were observed for this XLPE, but we observed that this kind of behavior is material dependent. In this Brand Rex XLPE, even at the highest temperatures, we saw more homogeneous aging throughout the thickness. So that's been a common theme when we've tried to look at these knowledge gaps, is that we can't paint with a broad brush the behavior of all materials. and say all cable insulation will behave a certain way because these different, as you might expect, if you look at what they're made out of, these different formulations have different chemistry, and they're going to behave differently when they're exposed to environmental stresses over time. So I'll go quickly through these slides. In this effort, we measured tensile properties, elongation of break. So you see that the elongation of break values, how far you can stretch the material before it breaks, tracks with temperature. At the higher temperatures, you can't. It takes a shorter amount of time for that elongation break to fall off. We didn't. Here's the tensile strength of these materials. So we tried to measure these macroscopic mechanical properties, and then we looked at try to correlate them with the effect of aging through the thickness of material. Here's a few techniques that have been used historically to look at this inhomogeneous aging, meaning the aging doesn't happen the same throughout the material. These are through the thickness of cable insulation. So these are low voltage cables, so the thickness of the insulation is on the order of a couple millimeters. And here's the interior and the exterior of the insulation sample. These were aged with the conductor removed. So we have aging on the inside that's similar to the outside. And so in this case, we looked at scanning electron microscopy with electron diffraction spectroscopy to look for oxygen concentration through the surface. And we saw, so we could see when it was greater at the edges than in the center. We used an FTIR microscope to look at carbonyl index through the thickness, to look at oxidation near the edges. And then we used a technique that similar to what's been used in the past to look at mechanical differences across the thickness. So this was, we used a nano indenter to look at hardness values throughout the thickness. As the polymer oxidizes, the hardness increases. So we mostly use those techniques to validate our use of color change. Here's a process for the FTIR microscope where we took a cross-section of a sample, we polished it to get a nice flat surface, and then we measured the infrared spectra at various locations through the thickness. And there's a peak that corresponds to the carbon double bond oxygen, that bond that forms with oxidation, and that peak increases with oxidation. And the carbon-carbon, carbon-hydrogen bonds correspondingly decrease in quantity. And so the ratio of those two is a carbonyl index, and that's a way to trace oxidation as a look. We're able to do it with this microscope, do it as a function of location to that thickness. Here is the new technique we developed using a color change on these similar samples. As cross sections are polished, we're able to image the whole slice of the cable insulation all at once, and then quantify the color change locally there with just optical microscope resolution. And then we can track, normalize through the thickness of that insulation to look at the behavior across the thickness. So that's how we pursued it. Here, these are a little different plots than on that first one I showed, where they showed all the temperature on the same plot. These have a different plot for each temperature versus time of exposure. So you see that this inhomogeneous behavior also evolves with time at given temperatures. At low temperatures, it in general happens less severely than at higher temperatures. But these plots, these were calculated using a color change, show that aging as a function of location through the thickness of the material over time. And one of the goals here, which worked reasonably well, was to try to compare normal activation energy. Normal process for calculating activation energy is often done with this tensile elongation and break, and compare that with activation energy that you might calculate if you're just looking at the interior of the cable, of the material. So if this DLO artifact of accelerated aging is really throwing off your lifetime prediction, then you might be able to see that if you predict the life from the interior of the cable versus the exterior of the cable. So for these three examples, we compared activation energy derived from the EAB versus derived from the color change, and we saw some some differences. And one, so this is, you know, these are just one data point limited to what we looked at. But in this example, we saw a decrease in the activation energy compared to what you would expect from the EAB. So that might be a point of concern that maybe the cable is not going to last as long as you think it is if you're using a technique that doesn't account for these artifacts that happen during accelerated aging. Any questions on that in homogeneous aging part? All right. Yeah, I hope this is interesting. So I'll show a couple other brief summaries of, we're looking at the knowledge.
Leo, sorry, it's the fact that the microphone is muted, so you do not actually listen to us. Yeah.
All right.
Anyway, I could ask you that I mean, I tell you that you should have like 5 minutes left. Would it be okay?
Okay, no worries.
Okay, thank you.
All right, 5 minutes left. Here we go. So we similarly looked at the effect of gamma radiation and thermal stress as a function of the order with which they were applied to the material. We did a temperature aging, thermal aging first, and then radiation, or the other way around, or if we did them simultaneously. And we saw that through different measures of aging, that the lifetime of that cable material was affected by the order of exposure. And again, the take-home message was we can't say all materials are going to age more quickly when you do it in a certain way. It turned out it was material dependent. So in some cases, we saw that the sequential exposure was more severe than the simultaneous exposure that you might see during a cable lifetime service in the plant. And then sometimes we saw it was less severe. So that you have to look at the details of the material to make those predictions. So this is further along that line of work, and the conclusions are the severity of the sequence of exposure is material dependent. And that's, you know, one of the concerns was in a plant, these cables are going to get exposed to gamma and heat at the same time, whereas accelerated aging, you're going to have one after the other. And so if that simultaneous exposure is more severe, then we are overestimating lifetime, and we're going to have more failures than we're anticipating. But one of our conclusions was that's not necessarily the case. In some cases, the simultaneous exposure was actually less severe. So what we're planning to study this next coming year is this so-called inverse temperature effect. We have exposed cable samples in our facility here at PNNL with a cobalt-60 gamma source. We exposed 3 different sets of cables samples at 3 different temperatures, but all at a common dose rate. So we did a 60, 90 degrees and room temperature, all at 100 gray per hour. So we're going to be comparing the effects of a series of different doses on those materials at those different temperatures to look at this inverse temperature effects. So with my 5 minutes left, I will quickly show you that's the cable aging technique. Cable NDE task we have is looking at trying to understand the state of the art for commercial NDE available to operators, including local and bulk NDE towards better cable life prediction. So bulk is commonly what's going to be available is testing from the terminals at the end of a cable, like the dielectric spectroscopy or tan delta. That is going to, so we can develop more sensitive and techniques for doing that and understand them well. That's going to be useful. And the trend is really towards reducing the labor involved in that. So for instance, if you can avoid disconnecting the cables, for instance, from motors before testing them, that'll save much labor in the testing. And then ultimately we need to move towards online testing where we don't disconnect the cables at all, and we continually monitor the cable health over the operation of the plant, not just during some little time stamps during the outage. So definitely the move is towards online monitoring, and a step in that direction is just being able to test cables with minimizing the amount of disconnects that are occurring. So we've been looking at that. Currently, we're looking at that at PNNL, testing cables that are connected to, well, we're planning to look at that tech we have already connected to the motor or not connected to the motor, and try to understand the signals from those tests in those scenarios. Local tests are ones that you might do with if you have measuring a denter modulus, or using the portable FTIR, or so these are when you can see a color change in the cable when you can touch it during cable walkdowns. These are often what's quickly measured when you walk through a plant and look for signs of stress. But of course, they're severely limited by what cables are available to look at. The buried cables, the big cables and walls are not going to be available. So some of the cable NDE advancements that we have done at PNNL is we compared to different commercial instruments for frequency domain reflectometry. There's one from Lyra wire scan Lyra instrument that's sold by Fauski and Associates in the U.S. We compared that with the FDR on a AMS Care instrument from this company in Tennessee, and then with just the laboratory-built vector network analyzer results, and we saw very similar results upon those using those different technologies. We've done some finite element physics-based modeling of FDR responses and towards understanding the effect or the signals. So when you get a signal frequency domain reflectometry, when there's a defect, if that change in impedance that you're monitoring is uniform change, or if it's a tapered change, that affects the shape of your signal. If based on the frequency you're using, the size of that defect can split your signal into multiple peaks. So that understanding is very important as you're trying to make sense of your NDE signals. So these up here just shows that our simulated signal and our actual measured signal for damage to the cable is very similar. So our simulation was working. Finally, this is another example for this NDE section. Another example of this is a local technique, is a so-called interdigital capacitance. This is where you have a interdigitated electrodes sensor you can apply to the surface of the cable, measure the dielectric properties underneath the sensor to see if they're changing over time. This has historically been used to look at, most cables are jacketed, so you look at the change in the jacket polymer versus the insulation. We demonstrated along with colleagues at Iowa State University, and now we're exploring this with University of South Carolina collaborators, that when you have an unshielded cable, by judiciously selecting the geometry of the electrodes, you can actually detect changes in the insulation through the jacket. So you can see changes in the jacket and the insulation just from the outside with these sensors if you don't have a shield. So final comments to wrap up. So the reason why subsequent license renewal is important is because this is for the US. Our electricity generation capacity from nuclear from the original 40-year licenses are all going to go away because we're not building new plants very rapidly. With license renewal to 60 years, it's going to last longer and eventually it's going to go away. But it's important for us to think about how long we can use reactors in the US and elsewhere as we move forward, and we want to continue to have nuclear low carbon electricity as part of the mix. So continued use of aging cables is going to need cable aging management programs that are effective. We're going to need to understand how to slow down aging when we see it happening, mitigate cable aging. There's some commercial company that looks at technologies to rejuvenate cables, to treat them so they can extend their life with chemical treatments. Methods to monitor cable aging and moving towards online monitoring are very important. And then I think it's going to be increasing opportunity for digital twin and other kinds of simulations to understand cable signals. A true thing in cable condition monitoring is that no single test can give you all the information you need. And being able to understand how to relate the results of multiple tests, I think simulation can help with that. And then we need to validate new techniques that are coming up. Dielectric spectroscopy is very promising. But for example, we need to be able to validate that. And so I will just summarize. We have a capability at PNNL called the Arena Cable Test Bed that we're using, where we have, like I mentioned, cables connected to motors or not, or through an oven or through a water bath. And it's a good opportunity to validate new techniques and develop new condition monitoring techniques towards online monitoring, and then try to understand combining our cable aging and cable NDE supported by the DOE to understand what those signals mean. When you get a FDR gives you a local change in impedance, you might see. DS shows you a change over the whole cable. So putting those kind of signals together to understand what is the nature of your degradation and where the location of it is, I think there's a lot of potential there that we can use simulation and digital twin and machine learning, and those are kind of other tools to increase our effectiveness and efficiency in cable aging management. So I'm glad to entertain any questions you might have, and I thank you for the opportunity to share with you some of the work we've been doing.
Thank you, Leo. I think it was a really interesting presentation, in particular the fact that actually both Europe and US are trying so hard to extend the life of these nuclear power plants in the framework of a low carbon world, let's say. So now the floor is open for questions. Sebastian, please. Yeah, if you can, it's better because the mic is here.
Thank you, Leo, for your presentation. I had a question about the data you presented for the density measurements. I will just sit down so you can see me. Especially the slide you presented where, yes, exactly this one, the previous one, where you presented the data collapsed with the property P. Yes, normalized property. Do you have an idea why the density measurement does not come onto this well-defined straight line in the middle? And maybe related to this question, the value that you measured for XLPE, do you think, I think it was around 1.3 or 1.4. Was it okay with you?
Oh, was that the number we were expecting?
Yes.
Well, that's a good question. I'm not sure what number we're expecting there. Yeah, like I said, I was a little bit surprised because I was under the impression that density was one of these sensitive measures that would track well with aging. And that it might be more fruitful than tensile measurements. We have situations like a bonded jacket, we have complications. In our case, why we didn't see, so there's some limitation to our sensitivity of our balance where we measure the density, but even with our variation, I'm not sure if we saw near constant density over what we were examining because of competing factors that might be decreasing or increasing the density. I don't know why that is. So in this case, it was radiation only, no thermal stress, but we definitely saw the mass change. So that means if the density is constant, we saw the mass change, we must have had a volume change as well, but we didn't monitor a volume change.
Yeah, because even the initial value was a little bit high. Is it field XLPE or is it?
Oh yeah, right. So that's a good. So when people talk about the behavior of XLPE and EPR, those are shorthand. These are really composite materials. They're not just a polymer. In fact, many of these materials have 50% or more inorganic filler. That's right. So when you're thinking about polyethylene, the density is much lower than 1.4. You're right. But when these have, this XLPE, for instance, it has antimony in it. It has many additives that are denser than the polyethylene itself.
Okay, thank you for your answer.
Okay, thank you. Ignacio Marcello from Spain. I will ask one question to you. Regarding this slide, I understand you have harvested the cable of the right, the EPR. And this EPR has 15 years, but 15 years of operation of 15 equivalent years, because it's very, very different. Normally, when you harvest a cable, you have two problems. That the first one is the difficulty to determine if the jacket is adequate or was destroyed by the harvesting process. And the second one is that normally you harvest the cable in a better condition than the worst condition of the plant. Normally the area with higher irradiation and higher temperature is very difficult to extract the cable. And normally you extract the cable, but you don't know if it's really the worst or it's a better condition. And normally the equivalent year are very low compared with the real year of operation of this cable.
Yeah. Yeah, thank you. Like I said, it's hard to do 40-year experiments on cables, but what we do have now that they didn't have at the beginning of the nuclear activity was operating experience. So there are plants that have been operating for decades. So harvested material is one way to get actual samples that have been actually exposed over that time. In this case, the XLPE we were looking at was new. We purchased it a few years ago. The EPR was harvested. The 15 years corresponds to how long it was installed, not how long since it was manufactured. It was actually installed at Crystal River 3 for that long. But like you said, a challenge. Oh, here the slide I want to go is here. So it was another surprise to me was that the actual environments in plants are not as well known as I would have thought. When we get a cable from a plant, say there's a plant that's changing out cables or is being decommissioned, seems like a great opportunity for us to get materials that have been in service to understand the effect of that service life and understand if it matches our expectations or not. But a challenges to that plan is that if you just get this old black cable, you may not even know what it's comprised of. And you may not know what its service history has been. A lot of times there's sales paperwork, so you know when it was installed. But it's surprising to me that it's not that always that well known what the temperature or humidity of the environment was, or the dose rate where that cable was extracted from. So you can if you know what part of the plant it's extracted from, you might be able to infer whether it's going to have any or high dose rate or not. But surprisingly, that was one of the knowledge gaps, is if we start to say, well, these assumptions were used in the qualification, but they're more extreme than the actual environment. Well, what is the actual environment? So EPRI has had a report out, and they've done a couple of efforts to try to get actual plant conditions for a BWR and for a PWR. And so they've, in one case with the BWR, they used data from a plant that had actually recorded that over time. And in the PWR, what they did is they installed sensors all over a camp during a plant during one operation cycle, and then they kind of try to infer from that, well, for over 40 years there's so many cycles and this is what they've seen. But they're definite challenges to using harvested material, because you may not know much about the material itself, and you may not know about its conditions. And then to your other point, whether or not the piece you get well represents what it saw in the plant, that's another question. My colleague Bill Glass, he's more interested in getting cable samples from plants when there's been an issue, when there's been a defect or a failure, because it feels like that's what's going to inform us more. I think that's good. I'm also interested in getting just material, so I know, okay, here's a 40-year-old material, but knowing where it came from, or it's a challenge. And it's expensive to get that information. The operator, maybe they're tracking their cables over time because they have to, but like in the US, we've had several plants close down in recent years, and it seems like a good opportunity to get some of those materials. But when a company has a contract to operate the plant and it's going to close down, they transfer that to the demolition company, and all the people that knew about the history of the cables might be gone. The demolition company doesn't doesn't care about getting nice, clean samples for you with information about them. They just care about taking the plant to the ground. So it can be expensive, if at all, to get that information. So there's a difference of opinion. NRC would like for us to have more harvested materials to data from harvested materials, especially for other things like the concrete or the reactor pressure vessel materials in the plant. But there's a mixed opinion about whether or not it's worth monetary investment to get those materials based on what information we get from them because of some of these limitations.
Thank you very much. I have an additional question. You have tested PVC?
So we haven't tested PVC very much. When we have, it's because it was a jacket on like EPR cable that just coincidentally had PVC jacket. And when we do thermal aging on a PVC jacket EPR material, naturally the PVC jacket degrades more rapidly and falls apart before the EPR does. But in one, I don't have a slide of it here, but in that case, when we've also, so I mentioned this carbonyl index is an FTIR signal for aging. We've also looked at something we call the dehydrochlorination index, because in those chlorinated polymers, it's the chlorine leaving that's a good FTIR signal versus the oxygen coming. But we haven't done a lot of research with PVC.
Yeah. The problem is that PVC, the conventional technique, non-destructive technique, for example, including the LIRA, could not provide any extra information about the aging. It's very difficult to follow the aging of these cables.
Yeah, that's my understanding. So we've tried to focus on the most prevalent materials in the U.S. plants, but that's my understanding is that is one distinction, is that maybe in Canada and in Europe, PVC is a lot more prevalent than it is in the U.S.
Yeah, this is okay. Thank you very much.
Thank you. Is there any other question from Bertinoro?
I'm sure it's been a long day, but I encourage you, if anyone has any questions later, feel free to reach out to me anytime.
Thank you, Leonard.
Simon, can I ask one question?
Yeah, sure. Go on.
Yeah. So, hi, this is Konsta Sipilä from VTT Technical Research Center of Finland. This was a really interesting presentation. Thank you. You mentioned about rejuvenation of cables, and it's some kind of chemical treatment. What kind of chemicals you actually use, and in which extent you can rejuvenate these cable material properties with these chemicals?
Yeah, that's a good question. So that's a kind of a different angle here. So outside of the nuclear industry, cable rejuvenation has been used to treat, I don't know, 1 million miles and thousands of miles of cable. It's used much more commonly outside of nuclear. I don't know exactly what it's like in Europe, probably similar. In the nuclear industry in the US is very conservative, and it's very difficult to change materials or change techniques versus the ones that have already been put in place. So that's one reason why it hasn't taken off as much in nuclear. But in distribution and other cable industries or examples of uses, rejuvenation has been used commonly when there's, most commonly it's been used for medium voltage cables that are maybe difficult to replace, like maybe they go under a waterway, or they're buried cables. And so rather than the cost to replace them, you can spend, it's not free, but a portion of the cost to rejuvenate them. And so often, historically, it's been used to address water treating in cables, so medium voltage cable degradation mechanism, and the so the process involves injecting a fluid into maybe inside the jacket, and so it fills the interstitial spaces between the insulation and the jacket, or maybe it's even in the conduit. I'm not sure about that, but most historically, it was originally technologies developed by Dow and then others have involved silane chemistries that react to cross-link and even react with if there's any moisture in the polymer, and they basically make it more hydrophobic and keep the water away so that it's able to maintain or even recover dielectric properties there and keep the water away. So it's most often been used to overcome moisture damage. And so for maybe 80%, it's not cheap, but maybe 80% or less of the cost of replacing the cables, you can pay the company to come and rejuvenate the cable, and then they give a 10 or 20-year warranty on it. So that sometimes it's worth the operator to do that. We have had some initial efforts in the past to look at rejuvenation techniques to try to recover some property loss due to thermal aging. So for instance, if there's been bond scission and breaking of polymer chains within the material, if you can introduce some chemistry that can soak in and cross-link, maybe you can recover some of those properties. Another degradation mechanism, like for PVC, is the plasticizer leaking out of the material. So a lot of times that leads to degradation of properties. So you can rejuvenate that in those cases by imbibing plasticizer back into the material. So those are some of the thoughts related to rejuvenation, is to try to recover some of the lost properties. I make that distinction between that and mitigation. So mitigation, maybe you're seeing that you're concerned the polymer is going to age in its environment, or you're seeing it's already starting to age the cable. So then you do something to kind of halt that or slow that down. But rejuvenation, the idea is to actually recover some of that. So I know the IEEE Insulated Conductor Committee has had some efforts to try to look at standards around rejuvenation. And there's been a lot of big effort by those commercial companies to penetrate into the nuclear market, but it still has not been used a lot into nuclear.
Okay, yeah, thanks.